Okay, so now that we have talked about the definition of our axes, right? Specifically, we've talked about the importance of defining an increasing x direction because velocity is a vector. We are ready to describe the particle's motion. So the particle will trace a path in space, and this path can be described as a function of time. So if we talk about 1D motion, right, the particle is restricted to move in a 1D line, and after putting out down our direction for increasing x direction, the particle's position can be described as a function of time. So perhaps at this time, let's say t equals to 0, x equals to 0, then perhaps at, let's say, t equals to 1, x equals to 2, let's say at t equals to 2, x equals to, let's say, 9, right? And then maybe, let's say, the particle starts coming back. So let's say at t equals to 3, the particle is back at, let's say, 5, and after that, let's say at t equals to 4, the particle is back at the origin. So this, in general, if we plot x as a function of time, if we know the function x of t, right, and that means that if we know how, if I plug in t, it will give me a value of x, then we kind of automatically know the entire life of the particle. We're literally following it everywhere it goes, right? We know everything that it's up to. We know where it is at every point in time. And so the goal of kinematics, or the goal of physics in general, is to solve for the particle's position as a function of time. This is not always necessary. Later on, we'll talk about conservation of energy, where we actually do not need to know where the particle is at every point in time. Maybe we can know the velocity, right? But in general, if we do know the particle's position as a function of time, we know everything about the particle. All questions that we possibly want to ask, we know, we can calculate it from this function. We have solved for the particle. We know everything. Yeah. So an example would be, if I know, let's say in 2D motion, if I know the particle as a function of time is 2t minus 5t squared, this kind of corresponds to throwing a ball up and down, right? Because initially it's moving up with velocity with a speed of 2, choosing up to be choosing up to be the increasing y direction, right? This corresponds to throwing the ball up with an initial velocity of 2 and letting it be pulled down by gravity, right? Which is why the minus 5t squared is here. This is just an example of what I mean when we say we solved for the particle's motion. We know the analytic expression for the function s of t, right? Yeah. So now that we've defined x as a function of t, now we define position as a function of time, it leads us to the SUVAT equations. So as I mentioned in the first video, acceleration is the derivative of velocity, and velocity is the derivative of position, right? So acceleration is the second derivative of position. So from these two definitions, right, it's actually possible to derive all of the SUVAT rules. So your teacher will probably have gone through a lot of the SUVAT rules, but I don't really, in my personal opinion, right, this is clear from the definition. This is also clear from the definition. And this is the third one is the only SUVAT rule that I feel is worth memorizing. The other two, I've never really used it in my physics Olympiad journey before. Yeah, but that's just my honest opinion. So, but how do I solve questions if I don't use the other two a lot? I actually look at the velocity time graph. So I'll describe why this method works for me and why you should use it too. And yeah, so from the two definitions, right, velocity being the derivative of position. So instead of x, sometimes we write s, right, to represent displacement, right? Same thing as s, same thing as x. And acceleration to be the derivative of velocity, And for 1D motion, for SUVAT to apply, your acceleration must be a constant. So acceleration is a function of time, right? As a function of time alone, there's no saying that it must be constant. But if we impose that the acceleration is a constant function of time, meaning the acceleration doesn't change with respect to time, then if we plug in this into the if we plug in this into the definition of acceleration, then we can see, if we plug in this into the definition of acceleration, you can see that the velocity, right, v of t, is just the integral of acceleration with respect to time. And because acceleration is a constant, it's just some constant a naught. This is just a naught t plus some constant c. But instead of writing c, where c is the arbitrary constant, we write v naught, where v naught is the arbitrary constant. And the reason why we write v naught is because you see that this is v is a function of time, right? This is v is a function of time. This v is a function of time. If I had written c over here, we want to understand what that c means. So suppose I written c over here. What does this c mean? To find out what c means, we kind of want to eliminate this other term. So we substitute in t equals to 0. And if we substitute in t equals to 0, we realize that v of 0 is equals to a naught times 0 is just 0. So this is just 0 plus c. You see the c is v evaluated at 0. Velocity function evaluated at the time t equals to 0. And this implies that c, physically, it means the initial velocity. So remember that when we do the integration over here and we get that c is an arbitrary constant. Right? That's the math side. We get c is an arbitrary constant. But arbitrary constants in the math, it must mean something in physics, right? It must mean something in physics. And to extract the physics behind this constant c, what the physical meaning of this c is, we found that we substitute in t equals to 0, c corresponds to the initial velocity. Initial meaning t equals to 0, velocity. And usually initial velocity v0, we denote it as v subscript 0. So I could have written, so that's why I substituted back in. I could have written v0, but usually we prefer to write it as v subscript 0 because we don't want to appear like a function is, we don't want it to appear like the definition of a function. It depends on the function itself. Yeah, this is just a constant, and this is the final expression for velocity. So you can see that from kinematics and this definition of acceleration, right? If our acceleration is constant, then we get the first SUVAT rule. Okay, so what about the second SUVAT rule? Right? S is a function of time is just the integral of velocity as a function of time. And we know velocity is a function of time is given by equation 18. So we just substitute it in. Wait, sorry, this is a naught dt, and a naught and v naught are just constants. So integral of this is a naught t squared times half plus v naught t plus, once again, there's an integration constant over here. But if we look at what the physics is behind the constant of integration, right? If we substitute in t equals to 0 into this s of t, we can see that t squared disappears and t disappears. So these two terms disappear if we substitute in 0. And that leads us to conclude that c, the constant integration, corresponds to the initial position of the particle. And that's how we arrive at equation 19. Okay, so yeah, so this gives us the first two SUVAT rules. So let's talk about the other SUVAT rule. So equation 13 and 14 and 15, okay, I will not derive equation 14 and 15 because I don't feel it's important. But let's derive equation 13. Equation 13 is very useful. So the geometric intuition for equation 13 or the SUVAT rules can actually come from understanding the geometric intuition for integration and differentiation. So the trick is to plot v as a function of time. So v of t, right? If the acceleration is constant, that means that velocity must be linear. So I cannot have a velocity that looks like that. right? Because acceleration must be constant, meaning that the gradient of velocity must be a constant, meaning that the possible velocities are only straight lines. Okay, so let's say this is v of t equals to a naught t plus v naught. Right, v naught would be the y-intercept over here. Right, v is a function of time, so t equals to 0 corresponds to here, and a naught is the gradient of this velocity time graph. So the reason why I like the velocity time graph is because velocity is nicely sandwiched between acceleration and position, right? Velocity is the derivative of position, and velocity is the integral of acceleration. So that implies that if I want to find the acceleration, right, I just need to take, if I give you the graph of velocity with respect to time, and I ask you what is the acceleration, you just need to calculate the gradient of this linear graph, right? Very easy. If I give you the velocity time graph and I ask you what is the position as a function of time, you just need to perform an integral, because position is the integral of velocity with respect to time. And what is the integral in this case? You actually do not even need to perform the integral, because velocity time graph is a linear function, which implies that all our integrals, right, all the integrals are just areas of trapeziums. So we see this with all the examples, all the SJPO questions that we're going to go through. But I like the velocity time graph because if you know the velocity time graph, right, it's very easy to see both acceleration as well as position or displacement in the graph. So if I plot the velocity time graph, you kind of can see everything, right? You can calculate, you can see the initial velocity, right? You can see the final velocity, you can see the acceleration, you can see the displacement. It's all nicely wrapped up in this single graph. And you can even derive the v squared equals to u squared plus 2as rule. So to see that, let's just derive it right now. So after deriving this, we'll go on to a few questions, but let's first derive v squared equals to u squared plus 2as. So u squared is the value over here, right? So I'm choosing some time t from t0 to t1, right? Sometimes t, but I don't even need to know t0 and t1. I just need to know that the velocity at t0 is u, and the velocity at t1 is v. Then S is the area. And the gradient is A. Right, the gradient is A. So in other words, let's just remove all the useless information. In other words, we have our definitions over here. We have our velocity, the final velocity, right? Our final velocity. We have our initial velocity with our gradient, and our area. This is just the trapezium rule. So to see so, right, S is equals to the area of a trapezium is half times the base times the base. Okay, let's call the base delta t, or let's call the base t. Let's call the base t. Half times t times the sum of the heights, u plus v. And u plus t, the observation is that gradient a is equals to v minus u divided by time. So that gives me, rearranging, gives me t is equals to v minus u over a. And so substituting this back into here for t gives me s is equals to v minus u times v plus u over 2a. And this gives me 2as equals to expanding out v minus u times v plus u is v squared minus u squared. And rearranging finally gives me v squared equals to u squared plus 2as. So the reason why I like the velocity time graph so much is because you can see all the quantities u, v, a, s, right? And you can see t also. T is being the time. And by looking at the graph and calculating area of trapezium, you can derive the third SUVAT rule. And actually you can derive all the other SUVAT rules just by looking at some trapezium. The entire motion is kind of captured in this trapezium. And that's why I like the velocity time graph. And for the next few exercises, I'll be using the velocity time graph to go through them.